Hi, and welcome to This Week in Science and Technology. Today I'm going to introduce you to the equations associated with modern mechanics. Also, I'm going to start to compare modern mechanics to its classical mechanics cousin and to relativity. Because I use terminology specific to modern mechanics, I'm going to assume you're familiar with the prior episode where I introduced some of these key concepts. If you haven't seen that episode, you might want to start there first. I begin by placing the bus and the man on the street, forming a non-nested relationship. Now we put the bus in motion from left to right in a constant velocity. As explained last time, we can find out how far the bus moves by using the distance equation. Distance equals time times velocity. And when we add a distance to an initial position, let's call it x, we get a new position, x prime. This equation is called the translation equation, and it is one of the most important equations associated with classical mechanics. In fact, Einstein has a name for the motion this equation describes. He calls it uniform translatory motion. All this means is that the inner system is moving in one direction at a constant velocity, and that the new position is found using the translation equation. One note on terminology. In modern mechanics, both the inner system and the oscillating system can move. So technically, both can be referred to as a moving system. However, to show how modern mechanics is related to these other models, I will use the term moving system to mean moving inner system. Now let's take a look at the man. I could develop another translation equation that helps us understand his position, but what I think is more interesting in this case is to answer some questions about how far he moves. First, I need to introduce a few terms. The length that the man walks from left to right is called the forward segment length. The length he walks from right to left is the reflected segment length. We can also find the amount of time it takes for the man to travel each of these lengths. These times are called the forward segment time and the reflected segment time, respectively. Things get very interesting when we place both the bus and the man in motion at the same time. Mathematically, if the length of the bus is x prime, then we can find the forward and reflected segment times, and we can multiply these segment times by w to find the corresponding segment lengths. With these equations in hand, we can use them to answer questions about the distance the man walks. Well, almost. There's only one problem. We don't know the length of the bus. But don't worry, we know how to find it. If we make one key assumption, which is that when time is 0, the back of the bus is at the origin. So we can use the translation equation in reverse to find x prime. The equation is x prime equals x minus v times t. This equation tells us the previous position of the front of the bus, and our assumption allows us to use this position as the bus's length. Now we can use the length and time equations we just developed. Before I wrap up, notice that the forward segment length is actually one of the Doppler equations, and the reflected segment length is the other. All that's required is to replace x prime with lambda, which is the symbol that's used in math and science to represent wavelength. For now, I'm ignoring an important subtlety, which I'll need to address later when I take a closer look at relativity, but it's important that I show that modern mechanics is able to explain what classical mechanics explains today. So in this episode, I've introduced you to some of modern mechanics' key equations, and I've shown how modern mechanics and classical mechanics make the same predictions for the moving inner system and for the Doppler shifts. Next time, I'm going to use modern mechanics to explain the key conceptual and mathematical mistakes in Einstein's work. Until then, I hope that you'll continue to share what you're learning here and on my website with your friends and colleagues. I'm Stephen B. Bryant, and that's This Week in Science and Technology.